Just as the X-15 defined the second decade at Dryden, the Space Shuttle defined the center's role within NASA 2 decades later. The approach and landing tests of the prototype orbiter Enterprise brought a level of attention to Dryden that exceeded even that of the X-15 era. The Enterprise was to be launched from the back of a modified 747 airliner, with the orbiter gliding to a landing. The approach and landing tests, or ALT, would validate the vehicle's low-speed aerodynamics and systems, including the orbiter's fly-by-wire control system. Early in the morning of August 12, 1977, tens of thousands of visitors streamed onto Edwards Air Force Base and lined the east shore of Rogers Dry Lake to view the first free flight of the shuttle. After taxiing from the mate-demate device and taking off from the main runway, the orbiter 747 combination climbed to 30,000 feet. With the orbiter on its back, the 747 went into a slight dive, and the Enterprise gently separated. As the 747 banked to the left, the Enterprise banked right and glided to a successful landing on Rogers Dry Lake bed. Two more free flights were made in the following months, each one with the aerodynamic fairing installed on the aft end of the Enterprise, intended for use during ferry flights to Kennedy. On the fourth flight, the orbiter's fairing was removed, and the descent was steeper and faster than on earlier flights. The fifth and final free flight in October 1977 was to demonstrate a safe landing on the Edwards main runway instead of the lake bed. Each side of the runway was lined with employees and guests of Dryden for a closer view. The release and glide were uneventful, but as Enterprise neared the runway, a problem surfaced. The fly-by-wire computer system had a slight delay responding to pilot commands, and rapid control inputs led to a pilot-induced oscillation, or PIO. At landing, the vehicle touched down on the main gear, then bounced back into the air. It touched down again, and bounced again more shallowly, then touched down again and coasted to a stop. Needless to say, the spectators along the runway, including Prince Charles, got more than they had expected. This PIO tendency was soon corrected with a Dryden-developed PIO suppression filter, that is, software changes to the flight control computer. Here, the F-8 digital fly-by-wire vehicle proved to be invaluable, testing various solutions until the best one was determined. 3.5 years later, in April of 1981, the excitement at Dryden was at a fever pitch again, with tens of thousands of spectators lining the east shore of Rogers Dry Lake, and 1,000 or more news personnel scattered around. A loud double sonic boom signaled the return of the Space Shuttle Columbia back from a 2-day mission to space. Edwards Air Force Base was and continued to be the primary landing site for the Space Shuttle until 1984. Since then, Edwards is considered the primary backup landing site for the shuttle. Between 1979 and 1982, Dryden successfully demonstrated a very unique aircraft called the AD-1. The AD-1 featured a wing that could be pivoted obliquely from 0 to 60 degrees during flight. Rather than sweeping both wings back to fly more efficiently at supersonic speeds, the whole wing of the AD-1 rotated, which greatly simplified the mechanical design. While the AD-1 was not specifically designed for high speeds, it demonstrated the concept for a possible future high-speed design. During this decade, aircraft efficiency became more important with the increasing cost of fuel. Projects like the KC-135 winglets and active and passive laminar flow control projects on the Jetstar, the F-111 and F-14 aircraft were explored. While laminar flow control concepts have not been used yet on commercial transports, winglets have had wide use on many Boeing and Airbus airplanes. New technologies for fighter aircraft were also being tested in this decade using two small remotely piloted aircraft called HIMAT, highly maneuverable aircraft technology vehicles. Only 23.5 feet long, it featured a close-coupled canard and an aeroelastic tailored composite wing, technologies used later in this decade on the X-29. The digital fly-by-wire control system used an autopilot to fly precise maneuvers to gather large quantities of quality data in a short time. HIMAT research brought about far-reaching advances in digital flight control systems, which can monitor and automatically correct potential flight hazards. The HIMAT successfully achieved its goals of a 100% increase in aerodynamic efficiency over 1973 technology and maneuverability that would allow a sustained 8G turn at 0.9 Mach and an altitude of 25,000 feet. By comparison, at the same altitude and speed, an F-16's maximum sustained turning capability is about 4.5 Gs. As a tribute to the HIMAT contributions, one vehicle now hangs in the Smithsonian Institution's National Air and Space Museum. In 1984, NASA and the Federal Aviation Administration, FAA, teamed up for a flight experiment called the Controlled Impact Demonstration, or CID. The project's goal was to crash a Boeing 720 airliner to test a fuel additive designed to suppress post-impact fire. The additive, called anti-misting kerosene, or AMK, demonstrated the ability to inhibit ignition and flame propagation of fuel in simulated crash tests, but researchers knew an actual crash would provide more realistic conditions. A special site was constructed on Rogers Dry Lake, and cameras were set up to document the test from every angle, including inside the passenger cabin for even more crash data. On December 1, 1984, with only test dummies, extensive instrumentation, and 76,000 pounds of AMK on board, the old Boeing jet, flown remotely by a Dryden pilot, Fitz Fulton, was crashed onto the specially prepared area of the lake bed. When the aircraft touched down, iron posts embedded in the lake bed tore open the fuel tanks. The results were surprising. The CID impact ended with a spectacular fireball, enveloping and destroying the aircraft and everything in it. With the FAA on the verge of requiring all U.S. commercial airlines to use AMK, the NASA test discovered that the additive didn't work. Once again, the benefit of flight test was realized. The X-29A forward swept wing program marked the return of the X-planes to Dryden after a 9-year absence. The two-phase program ran from 1984 to 1992. The first phase concentrated on the proof of concept at low angles of attack and high speeds. The second phase of the X-29A program, the high angle of attack tests, is covered in the fifth decade. Two X-29A aircraft were built as technical demonstrators to test a forward-swept wing with advanced composites, variable camber, and a thin supercritical airfoil. Also tested was highly unstable and highly augmented multi-surface controls that required an extremely high-gain, triple-redundant digital control computer with analog backup. The fiber strands of the composite aeroelastic tailored wing on the X-29A were specifically aligned to allow it to twist under load. The twisting relieved the loads at the tip, preventing structural divergence or breakage at high speeds. The digital flight control computer system provided sufficient artificial stability and predictable handling qualities in a very unstable aircraft. Moreover, its supercritical wing contributed to good maneuvering and cruise characteristics in the transonic range. Despite these accomplishments, the predicted higher lift-to-drag ratio did not materialize, being about equal to or slightly less than the then current fighter aircraft. The fourth decade brought much publicity to Dryden with the Space Shuttle flight's controlled impact demonstration and the revolutionary X-29A. Each of these projects came to Dryden from outside agencies for the world-class expertise and facilities. All were successful, though not always in the way expected. In the words of Hugh L. Dryden, flight research separated the real from the imagined problems and made known the overlooked and the unexpected.